Okay. So for question 2, are you there?
Yeah, we've got a lot of different stupid files we need to open up eventually.
Yeah.
Following is the best interpretation of a 90% confidence interval of heart rate between 45 and 105. Okay, so what do you think?
That's what I got.
Say what?
95 or 90% of all people have a heart rate between 45 and 105.
Let's see. You want to guess again?
Oh, um, oh, did I say? I meant we are 90% confident that the true mean heart rate is between 45 and 105.
Perfect. So there's
I wrote
two parts to the confidence interval: how confident we are, and the interval itself. And the point of the interval is we're trying to find the true population mean. So mu, we're looking for mu. And yeah, we can't say 90% of all people are going to have a heart rate between those two because that's a completely different topic.
Yeah, I actually wrote down we are 90% confident on my paper, but I guess it didn't make it all the way to the computer.
Yeah. And then the next one, 90% chance that the sample mean heart rate is between 45 and 105. Why is that one wrong?
Because we don't use the word chance. We use the word confident.
That is the answer for the fourth question, because if the true mean heart rate, the probability is either 0 or 1. You know, it's either 0 or 1, and we don't know what it is. We're making a guess here. So why is the third answer wrong? It's partially the same, but there's another reason why it'd be ridiculous to say there's a 90% chance that we know the sample mean heart rate.
Um, um,
So how does our sample compare to our population?
they are, well, depending on the sample size and stuff, like the larger the sample size, the closer the sample mean and the population mean will be.
And you actually got pretty close when you said sample size. So is there any way, let's say that we wanted to know the average height of all 320 million Americans. Is there any possible way that we could measure everybody and figure out the mean?
No.
Let's say that we take a sample, and like you said, high samples are good. Let's say we get a sample of 150 people to get that. Is there a way for us to measure 150 people and get the average of that?
Yeah.
Yeah, that's the whole point of taking a sample. So
Yeah.
to say that we're 95, to say that we have a 95% chance of knowing the sample mean is ridiculous. We have a 100% chance of knowing the sample mean.
Okay.
Yeah. So
Yeah.
you're totally right in saying that confidence intervals, it's not a chance, it's either 0 or 1. That's the probability of it occurring. So we have to say that we're confident. But in the case of sample means, that's the whole point of taking a sample, is that we can calculate the sample mean and extrapolate from that.
Exactly.
So does that make sense?
Yeah, that makes sense.
Okay.
Cool. And then 3. Okay, so this one was a little maybe, but I got no, the distribution of the mean of each sample is not normal since the sample size is not large enough.
Why does sample size matter? In general, why does sample size matter?
The more, sorry, the more, the larger the sample size, the more accurate your sample will be.
In what ways?
Um, like the larger sample size, the closer your sample will be a representation of the population mean.
Yeah, so the larger our sample size, the smaller the standard deviation is, which narrows the curve,
Mm-hmm.
which means that when we have
Standard
um,
deviation is smaller.
yeah, when we have a standard deviation of 1, that means all of the data is clumped together a lot closer than if we have a standard deviation of 25.
Mm-hmm.
So we can say we would end up having a 95% confidence interval that, say, the average height of people is between 5'6" and 5'8", and having that narrow standard deviation is a lot more useful than saying the average height for people is between 3 foot and 8 foot. So
Mm-hmm.
having higher sample size decreases that standard deviation.
Mm-hmm.
And then what's the other thing that it does if we have, and the number we're looking for is 30. What's the other thing that happens if we have a large sample size?
So the standard deviation is smaller. It's pretty much just that's the same thing what we just said. Oh, it's so obvious. I know what it is. It's the
The latter part I just mentioned was the law of large numbers.
mhm.
This one is from the central limit theorem.
Yeah. Mm. Blah, 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 blah. Trying to find where I wrote it down at. Okay, yeah. So we said the sample size is large and the sample mean will typically be close to the population mean. And then the standard deviation gets smaller, and with the sample size is large, the X bar will be approximately normal. So yeah, our population will be normal. So
Exactly.
even if, yeah.
So, wait, finish that sentence. Even if,
So even if the um
even if the
so if
population distribution,
yeah, so if the population, the parent population is normal, no matter what the sample mean will be normal.
yes,
But if it, okay, and then but if the parent population is not normal, but you have a large enough sample size, then your sample mean can be normally distributed.
yes. So having a
Okay.
large sample size will overcome that.
Yes.
So we have fairly small samples, just 15 and 10 or 15 and 20.
Mhm.
What do we know about their distribution though?
Um, does it say that they're normal? Oh, that they're approximately normal.
That's what the QQ plot is for.
Dang. Okay.
So even though our sample sizes are small, the distribution is still normal.
Okay. Are there
So that's the point of the central limit theorem, is that it states that if distribution isn't normal, you can compensate by making your sample size larger than 30. But in this case, our distribution was already normal. So 15 and 20 or 15 and 10 or whatever it is, I should just probably scroll up and not be lazy. But those are completely fine because it is, 20 and 15 are completely fine because it's already distributed normal.
Okay, yeah, that makes sense.
So in this case, increasing sample size is not going to help with distribution. It's not going to change the distribution to normal because it already is. In this case, what would increasing the sample size do for us that is beneficial? And this one is not central limit theorem. This one is law of large numbers.
Wait, so you're asking if we increase the sample size, what will it do?
Because having a large sample size, the larger the sample size is always better. There is never any drawback to having a large sample size, at least when it comes to statistics. The drawbacks come from money and time investments. Yeah. That's why every experiment doesn't do like 10,000 sample, people.
Yeah.
So statistically, things only improve when we go larger.
Okay.
So in this case, even though we're already normally distributed, what benefits would we get from having sample sizes of, let's say, 30 and 35?
The standard deviation would be smaller?
Exactly.
Okay.
So that would give us a more accurate confidence interval.
Okay.
Does that make sense?
Mm-hmm.
Perfect.
So it would be for question 3, yes, the distribution of the mean of each sample is normal since the data have been determined to be normal.
Yes. Okay. 4 types of confidence intervals listed below. Which one is appropriate for this experiment?
So I did have a question about this. There was a few other questions just like this. So I understand what an independent sample is, and I understand what a dependent sample is, and I know what it means when they say the sigma is unknown. But like, what is the difference between sigma unknown and an independent sample, I think was my question. Because it's like, for this, we would be using independent samples, but also sigma is not known. But we could just put it in Excel and find out the sigma.
What's sigma?
What is sigma?
Yes.
Sigma is the test statistic.
No, and that's why we wouldn't be able to put it in Excel. Standard deviation is the test statistic. So what is sigma?
Oh, it's for the population.
Exactly. So the population here is all men and all women, and since we're not given it, there's no way to figure it out.
Okay. So wouldn't it still be like, okay, sigma is unknown and we're using independent samples? I mean, can't they be in the same category?
Technically, it could be the case that sigma is known and we're using independent or dependent samples.
Yeah.
But the thing is, once we start moving into dependent and independent samples, we're moving into quote unquote more real statistics.
Yeah.
And anytime you go from the very first step of baby statistics that we did over the first 2 where they gave us sigma, it's just pretty much sigma is not known. Sigma is almost impossible to know.
Yeah.
So basically whenever we're dealing with independent samples, dependent samples, ANOVAs, some of the other things that we're going to be going over, it's pretty much just going to be sigma's going to be unknown, because we're dealing with hard statistics as opposed to soft statistics. But it's not impossible. We may do a confidence interval of the mean of differences of dependent samples, and they may just give us the sigma. So it's not impossible. Okay. It's just less likely to see.
Okay, so just stick with If they don't give you sigma, then sigma is unknown, and that will be the answer to the question, pretty much.
Yes.
Okay. So confidence interval of mu when sigma is unknown is the answer.
Sure. What are we
Am I sure?
measuring here? What's the null hypothesis?
Mm,
So it doesn't flat out say. So this is, you got to figure out what the researchers are trying to figure out. But what's the null hypothesis and what is the alternate hypothesis here?
So they're measuring the to-go, no-go stimulus and how they.
So get rid of to go, no go, because I don't like that.
Yeah.
Want us to determine reaction time in seconds.
Okay.
So just focus on reaction time and then read it and give me the null and alternate hypothesis.
So I guess the null would be that the reaction time for males and females are the same, and then the alternate hypothesis would be that they are different.
Yeah, perfect.
Okay.
What's another way to phrase that? That's just the convention for statistics when we're dealing with two samples.
Not equal to the null hypothesis would be equal to the alternate hypothesis would be not equal to, or is that not what you're looking for?
No.
Yeah.
What's another way to say that two things are equal? And this is mathematical jargon, but it is by definition the how they're using it in statistics. It popped up in the homework for homework 14, so I know it's going to be on the test.
Okay, I'm not sure.
Okay, so if two things are the same,
Uh-huh.
the two groups are the same, what does that tell you? How to phrase this without just giving it away?
Like dependent? Are you talking about like dependent variables?
Dependent or independent samples, it doesn't matter. When we have two different sample groups, so we're not dealing with ANOVA, but even when we are dealing with ANOVA, it kind of, whenever we're dealing with more than one sample group.
Okay.
Totally right. The null hypothesis is that reaction time of men and women are the same.
Mm-hmm.
There's another way to phrase that. And you're phrasing it in a mathematical term.
Oh, is it like weird? We have sufficient evidence.
They're not that far yet.
Okay. I don't know.
So how about this? Let's say you met, let's say, for example, you met Chris Pratt and Elizabeth Olsen. And someone was to say, how would you describe, how are they different? Describe them not by their own characteristics, but what sets them apart from each other? And I'm putting you on the spot, so you don't have to start listing things off. But
say the characteristics.
Yeah, so there's characteristics, and rather than saying Chris Pratt is tall, rugged, he's what was the term? He was. Oh, I love that line they use in Thor. It's like if an angel and a pirate had a baby. Have you not seen Infinity War yet?
No, not yet.
Oh, it's so funny. They're cruising out and they crash into Thor in space. So they, so they bring him on board, and Peter Quill and Chris Pratt immediately starts getting jealous because Thor is just perfect physical physique.
Yeah.
And so Peter's just like, what's going on with this dude? Why was he just floating off in space? And Drax is like, that's not a dude. It's like, what do you mean? It's like, you're a dude. That's if an angel and a pirate had a baby.
That's hilarious.
But anyway, so you can describe the differences. You'd be like, okay, well, difference-wise, Chris Pratt is heavier. He's got more muscle mass. Elizabeth Olsen has got longer hair. She's more petite. You know, you're describing them in terms of each other. You know?
Yeah.
Let's say that you had identical twins. So instead of Elizabeth Olsen, it's the Olsen twins. How would you describe the Olsen twins if I said, tell me how they differ from each other?
Their names.
Yeah, that's pretty much it.
Yeah.
But yeah, you'd basically be like, there's no difference.
Yeah.
So did that click it for you? Okay, I'm just going to come out and tell you. So the way you stated, there is no difference between male and female drivers, which is completely correct.
Yeah.
Another way to say that, so if you're saying like, there's no difference between Mary Kate and Ashley Olsen, another way to say that is that difference is equal to 0.
Oh.
Is that ringing a bell?
Oh. Yeah, like you're like yeah, okay.
Remember,
Yeah.
the way it's defined in the textbook is D bar. So
Yeah.
the difference between the means is equal to 0. And that's the null hypothesis.
Yeah.
And that's how we always do null hypothesis for samples of 2. And then the alternate hypothesis is D bar is not equal to 0, or D bar is greater than 0, or D bar is less than 0.
Okay.
But it's always when we're dealing with 2 samples, because you're completely right. The null hypothesis is that men and women drivers are the same in reaction time. But the way we state that in statistics is that the difference between the 2 means is 0. There is no difference.
Okay.
So that's just being more technical. But like I said, the reason I just wanted to hammer that home is because when I was going over the homework Sunday night, last night, there was a question that popped up that was, in fact, it wasn't even a multiple choice question. It was fill out the chart, and it gave the different tests that we've done so far. So sigma known, sigma unknown, paired, independent, and ANOVA. And it said to write out the null hypothesis and the alternate hypothesis for each of them.
Oh.
So I know that's going to be on the test. So just keep in mind that when we're dealing with paired samples, whether they're dependent or independent, the null hypothesis is D bar is equal to 0. And that's the same way as saying that the 2 samples are the same.
Okay. Okay. Cool. So question 4, the answer would be what did you get for 4?
You can't just palm this off me.
Oh.
Okay, so What's the null hypothesis?
That they're the same.
What is the same?
The reaction time for females and males.
But we don't phrase it like that in statistics. How do we phrase it?
The null hypothesis is they're equal to each other.
Equal.
Yeah.
What is equal to what?
The male and females reaction time.
Yes, but that's not how we stated it in statistics. How do we state it in statistics?
I'm totally drawing a blank. I can't do that.
We literally spent the last 10 minutes talking about this.
So D bar equals 0?
Yes.
Okay.
What is D bar?
D bar is when you have two samples.
But what's D bar? D bar is used when we have two samples, but what is D bar?
It's the difference the difference between the sample means.
Yes, exactly.
Okay.
So we know that our null hypothesis is D bar is equal to what?
0.
0. Okay. Another way of saying D bar is the mean of differences, or the difference between the means.
Yes.
So that narrows it down to 2 of the 4 choices.
Using independent samples.
Why independent?
Because the samples aren't related. Like, just because I pick, they don't have anything to do with each other.
Exactly.
Yeah.
What's a way you can make this different so that you're still dealing with reaction times between males and females, but it's a dependent sample?
We could do, well, later in the practice exam, they gave the example of siblings. And so
that's one way.
That would be dependent samples. Or like spouses or
like couples.
Yeah.
Okay, no, perfect. Yeah. That's exactly what I was looking for. So you understand that.
Cool.
Okay, question 5.
So obtain the balances of 90 bank customers rather than 30.
Yeah, hold on. I haven't finished reading the question. Which of the following would produce a confidence interval with a small margin of error? Oh, no, you're totally right. Because what's the equation for margin of error?
It is, wait for it. Sigma times z-score over square root of n.
And that's the key there, is over the square root of n. So as n increases, the overall number is going to decrease.
Yeah.
That's how math works. Okay, no, perfect though.
Cool. And then for this one, I got 1,000, but I don't think that's right.
Okay, let me check. 4 drive shafts, most of those are lengths and from for example, we need to be attacked with 1,000 millimeters. Lengths are known to follow normal distribution, so even though they're small, that doesn't matter. And we are given a standard deviation, so we do know the sigma. Okay. So put this one. Okay, so I just asked you a second ago, what's margin of error equal to?
Sigma times z-score over square root of n.
Okay. So
Oh, sigma.
sigma times z-score over the square root of n. What's our sigma here?
Oh, I think that's what I did wrong. It's 2.
How did you get that?
The standard deviation is 2.
Standard deviation is 2, and what?
Yeah, why did I do that math that way? Oh. Okay, I'm confusing myself. Hold up. But we don't have the z-score, so
Do we? What's the z-score?
it is something.
Well, actually, here's a question. Are we using the z-score or the t-score?
Z-score,
Using the z-score. Why are we using the z-score?
because we're given the standard deviation.
So we are given the standard deviation, meaning that we are given the z-score. Well, it means that we are using a z-score.
Yes.
Without even opening up the applet, what do we know about a z-score when our confidence interval is 95%?
It's going to be 0.05.
Where do you get that number?
Oh, wait, you're asking about, what are you asking about?
So when we have to,
Oh, sorry. So our alpha will be 0.05.
yes, alpha will be 0.05, and we're dealing with a z-score because we're given sigma. When we're dealing with t-scores, so the sigma is unknown, we have to put in our degrees of freedom in order to figure out what our t-score is. Since we don't have to put in our degrees of freedom for a z-score, we can just look at 95% and what's our z-score. The applet's there if you need to double check yourself, but this is one where we don't need the applet. It's just a number that.
I know what you're talking about. Hold the phone. So it's gonna be 1.96.
Perfect.
Oh, that's totally what I did wrong on this. Okay. Hold the phone. We got this. So it's gonna be oh 1.96.
Yeah, because it's just the z-score times 2, which is our standard deviation, divided by the square root of n, 4, which is 2. So 2 divided by 2 cancel each other, so our margin of error is equal to our z-score.
That makes sense.
And the next two should be pretty simple.
So it's gonna be 1001.96, and then it's gonna be 998.04.
I would put zeros at the end of those just because it says round to the three decimal places. I'm not sure if it would dock you for a zero or not. And also make sure you're putting the right number in the right question because you gave that wrong. First question is the lower bound.
Yeah, yours are right. Okay. So I totally just lost track of time,
Mm-hmm.
and I actually have to go to family evening. Um, are you busy tonight
Um,
to finish this?
is there a time limit on this? Could we just leave this open?
We can leave this open.
Okay. Um, it looks like, and I'm just looking at the window. I'm not sure if they're finished packing yet. And I have a project due in my computer science class that I really need my dad's help with.
Yeah,
So kind of depends. I should be free,
yeah.
but because it's just a simple thing that I can't figure out, but he should be able to do it with me in like 5 minutes. Um,
Okay.
so what time were you wanting to meet back up?
Like 9:30 at the latest.
Okay, that should work.
Is that too late? Darn, I'm so sorry.
No, you're good. That should work. If not, uh, things just got thrown out of whack because we got the truck today as opposed to tomorrow,
Yeah,
but we're still taking off Thursday.
okay.
So we can finish up tonight. As it gets close to 9:30, I'll let you know if we can
Okay.
finish up tonight. Otherwise, I'll shoot you a text and we can just do tomorrow at 6 o'clock our normal time.
Okay, are you sure?
Yeah,
I would just skip family meeting, but I kind of have to go tonight. So,
yeah. No, you're totally good. Like I said, I'm not sure if they're taking things out of the trailer. So I don't know if they're taking things out of the trailer to put in the truck or what's going on.
okay.
But if things just get complicated and I can't get my dad's attention, then I may be working on that project for a while and then we can just meet tomorrow at our normal time because
Okay.
uh, Tuesday, Wednesday, we take off Thursday morning. So tomorrow and Wednesday is just basically me working ahead in my
Okay.
computer science class so that I don't have to worry about homework on the 4 day drive.
Yeah.
So aside from that, I can totally meet at our regular time at six
Okay.
o'clock tomorrow.
Okay, I will if I don't hear from you, then I'll text you around 9 and maybe I'll get home a little earlier.
Okay.
Um and then we can decide from there. But I'm yeah, sorry. It's like my only obligation this whole week. It's like,
No, you're totally good.
oh man. Okay. Well, all right, I will text you tonight then.
Okay.
Okay, so sorry. I'm
Oh no, you're good. You're good. Don't worry about it.
okay. All right, we'll
Okay.
hopefully see you later.
Okay,
Okay.
bye.
All right, bye.